Hello, I'm Dr. Peter Hurley, the original developer of XID+, a probabilistic deblender we built as part of the Herschel Extragalactic Legacy project. This is a series of video tutorials where we go through and introduce the motivation for why we developed XID+, another video on how you can run XID+, going through an example Jupyter Notebook, another video on the latest iteration XID plus SED, which includes an SED emulator such that you can fit SEDs directly to the Herschel Spire maps. And finally, the process of building a probabilistic model, which is at the heart of XID plus, so that you can go away and make your own versions and iterations specific for your science question. So in this video, we'll concentrate on the motivation around why we developed XID Plus in the way we have. So the best place to start is introducing the challenge of dealing with far-infrared maps, and that's the confusion problem. Astronomy is multi-wavelength, in that different wavelengths probe different physical processes. In the optical and near-infrared, you can observe the starlight coming from galaxies, but those galaxies also contain dust, which absorbs some of that starlight and re-emits it in the far infrared. So if we want to get a complete understanding of star formation, or how many stars are being generated in galaxies, then we need to measure that dust emission. The problem, however, is as you go to longer wavelengths, you need a bigger and bigger telescope to get the same resolution as you do in the optical and near-infrared. In physics, we call this a Rayleigh criterion. However, there's a limit to the size of the telescope we can send into space. And as a result, the resolution of those far-infrared maps tends to be relatively poor compared to those taken in the optical and near-infrared. The animation in this slide is showing the same patch of sky observed in the optical, near-infrared, and finally the Paxton Spire instrument aboard the Herschel Space Observatory. And as you can see, as you go to those longer wavelengths, the resolution deteriorates. And that's what we call the source confusion problem. The challenge is working out which galaxies that we've detected or observed in the optical and near-infrared are contributing to that far-infrared map. But it isn't just a resolution problem. We've said that different wavelengths probe different physical processes. So being bright in the optical and near-infrared is no guarantee that you'll be bright in the far-infrared. So we're left working on the challenge of the bright blobs we observe in the far-infrared are coming from one or multiple objects observed in the optical and near-infrared, or possibly galaxies we haven't even detected in the optical and near-infrared. Now, traditionally, there are two categories of approaches in trying to distribute the flux to objects within these far-infrared maps. You can take the blind approach, which has the advantage where you will detect all the bright sources, but the disadvantage that you still have the challenge of then matching your blind catalogue to catalogues at the optical and near-infrared wavelengths. An alternative approach is the prior-driven approach. And there you take a galaxy catalogue that you can compile from different wavelengths, and you treat that as all the known galaxies which will contribute to the far-infrared map, and you distribute the flux appropriately. This has the disadvantage where if there are galaxies that are not in your original catalogue, which are bright in the far-infrared, you'll miss them. Now with XID Plus, we've taken the prior-driven approach. And we've taken that approach because for many of the fields observed by Herschel, the optical and near-infrared data is very deep and therefore contains most of the galaxies which we think will contribute to the flux in those far infrared maps. Now, in building XID+, using this prior-driven approach, we've decided to use probabilistic modelling because we think it's well suited for dealing with this source confusion challenge and has certain advantages over other approaches. So let's delve into some of the details around the probabilistic model and why that's appropriate and how it works. So a probabilistic model you can just think of as a mathematical model, but where we use probability theory. So you go about building a model which describes the data that you're observing in your system and includes all the parameters that make up your model and that can contribute to the flux. You then use probability theory to express all the forms of uncertainty around those components of your model and any measurement noise. Finally, you use inverse probability, or Bayes' rule, to infer parameters, i.e. go from data to estimates of parameter values. You can then adapt your models, make predictions, and more importantly, learn from the data. So at the heart of probabilistic models is Bayes' rule, or Bayesian probability. And that's an interpretation on the concept of probability which differs from which we're traditionally taught at a younger age. When we're first introduced to probability, we're normally taught it as an idea where you're thinking about probability in terms of frequency or propensity of some event, i.e. how many times you'll roll a 6 on a dice. Bayesian probability, on the other hand, treats probability as representing a state of knowledge or quantification of personal belief. I particularly like Bayesian probability because I think it makes people transparent to the assumptions they're making to their model. And more importantly, it gives us the full posterior probability distribution as an output. At the heart of Bayesian probability is Bayes' rule, which you can see on the slide here. And Bayes' rule is made up of traditionally 3 components. On the left-hand side, we have the posterior probability distribution, and this is normally the output when fitting a probabilistic model. And that's telling us the probability distribution for our parameter values theta, given the data we're given to the model and our model structure. Now this output posterior probability distribution is made up of 2 components. A likelihood component, probability of the data given our parameters theta and our model m, which is where we compare estimates from our model with certain parameter values to the data. And finally on the right hand side, a prior probability distribution, which is where we can quantify our belief about parameter values from the start, i.e. what values we know theta are allowed to take. So for flux, for example, that could be that flux has to be positive. So let's look at a simple example of a probabilistic model and stick to a straight line. So on the top there you can see the traditional equation for a straight line, y equals mx plus c, and then we'll introduce some additional noise component, epsilon. So here our parameters are m and c, the slope and the intercept. So let's go through the different components of Bayes' rule for the straight line. So we have the likelihood, the probability of y, our data, given certain parameter values m and c, and data x. And we have to assign a probability distribution to the likelihood. So for this example, we'll say we think the measurement error epsilon takes a Gaussian or normal distribution n. The second component, the prior probability distribution, allows us to quantify what we think those values are allowed to take for m and c. And again, you have to assign a probability distribution to that. So in this example, we'll assign a Gaussian distribution centered on 0 with some sort of uncertainty quantified by our covariance matrix, sigma. Combining that likelihood and the prior with a bit of maths leads us to the output, the posterior probability distribution. But you can see analytically, even just for a simple straight line model, the maths can be fairly complicated. So then the question arises, why are we bothering with all this Bayesian probabilistic stuff when naively it seems fairly complicated? Well, let's look at the advantage of taking this approach. So first, let's look at how introducing prior information helps us extract more information from the data. And we'll do that with using our straight line model, but introducing one data point, which you can see plotted here in our plot of y versus x. So with no prior information, the allowed lines have to go through that point, but can have any intercept and any slope. However, if we start introducing prior information, so for here we'll introduce it on the intercept, and we'll say that we think the intercept, or know the intercept, has to have a value of around 0.3, but that we have a slight uncertainty in that value, which we can quantify with the standard deviation of 0.1. Introducing that prior information alongside the data via the likelihood limits the allowed lines in our plot, and therefore gives us information on the allowed values of the slope. So this combination of prior information and one data point can help us constrain the slope, such that the probability distribution that we get as an output, which you can see in this plot, is constrained. So here we can see that the slope is most likely has a value of around 0.3 and 0.5, but with slight uncertainty, such that there's a slight chance it could be less than 0, and any value up to around 1. Now, the other key advantage of using a probabilistic model is that it gives us the uncertainty via that posterior probability distribution. And it's that uncertainty which is fundamental to the scientific methodology. That we want to understand the level to which our models are consistent with the data, and that requires a full understanding of the uncertainties. We don't want to know just the best answer, we also want to know how uncertain we are on those answers. So again, let's go to a simple example and show how having access to the full posterior probability distribution gives us that extra information. So on the bottom left-hand plot here, we have a 2D posterior probability distribution for our parameters A and B. And we have two posterior probability distributions, one in blue, one in red. On the top left and bottom right-hand side plots, we have what are called the marginalised 1D posterior probability distributions. And that's where we collapse that 2D space into a 1D space for both A and B. Now what you can see here is that the red and blue lines lie on top of each other. So if we were to just look at that 1D marginalised posterior probability distribution, we'd think those posteriors are the same. However, if we go back and look at that 2D distribution, we see that if the red posterior probability distribution, A and B are correlated, whereas for the blue distribution, there's no correlation. If there's correlation between the parameters, storing just the marginalised posterior distributions, such as in the top left, the bottom right-hand plot, which is what is traditionally done with catalogues, loses information. And here we're highlighting the difference in the information loss between blue and red. Capturing the full posterior probability distribution allows us to capture any correlations between parameters, and that correlation is information. It's even more important to have access to the full posterior probability distribution if that posterior is non-Gaussian. So in this example, we have another posterior probability distribution, again for parameters A and B, and we're looking at that 2D distribution with the different contours showing different densities. Now, the traditional approach of fitting models is what we call a maximum likelihood approach, and that's where you find the area which is densest in that probability space. However, if you take the maximum likelihood approach for this example, the green line, which you can see here now in this plot for a parameter A, naively you'd expect the probability of being on the left hand side of that green line to be 50% and 50% on the right hand side. However, because of this curved shape of this distribution, the line which actually governs 50% is shown in red, which, as you can see, differs from the answer you would get from a maximum likelihood method. And we could do the same for a parameter B here. Again, if you were to assume this posterior is Gaussian using a maximum likelihood method, the green line would find the densest area in this posterior probability space, and naively you'd expect the probability to be equal either side of that line, whereas actually the red line is showing where you have 50% probability either side. So curved posteriors easily occur when you're introducing things like positive constraints. And it's only by using these types of Bayesian methodologies where you can get a better handle on the posterior probability distribution. Now, astronomy obviously requires more than just straight lines. So how do we go about developing more sophisticated models which are suitable for deblending those spire far-infrared maps? Now, over the last decade or so, there's been an awful lot of effort and developments in something called probabilistic programming. And what that allows us to do is allows us as scientists to define probabilistic models and not worry about how you solve them automatically using Bayes' rule. So a good analogy is with coding. In coding, you have different types of languages. You can have low-level languages such as C++, where the code has to take more effort into working out memory management. And you have high-level languages such as Python, where you no longer have to worry about memory management and you can focus on building the model most appropriate for your area. And that's how you can see probabilistic programming. We can focus on just building the probabilistic model for our challenge. We don't have to worry about all the challenges and difficulties about what type of algorithms we need to fit them in a Bayesian approach. Another way of thinking about probabilistic programming is to compare it with a simulation. Simulations traditionally go from an input to an output, where the output is what we tend to observe, i.e. data. So you can think of a galaxy simulation where you have all the different types of parameters going into a galaxy, and then the output would be the fluxes for those galaxies. Well, a probabilistic program you can think of as a simulation in reverse, i.e. we have our model, which the simulation is based on, but we're going from data to parameters. Now, what's made probabilistic programming more accessible over that last decade is the development of different languages. And at the heart of those languages are more advanced algorithms. So you have your traditional Markov chain Monte Carlo algorithm, but more complex versions which can deal with more complex models, such as the known U-turn sampler based on Hamiltonian Monte Carlo, variational inference, and what most of these algorithms are now built on is something called auto-differentiation. So there's been advances in the algorithms which allow us to fit more complex models, but what's been really useful for us as scientists is the software which makes all this more accessible. And over the last decade we've seen user-friendly software such as Stan, PyMC3 and NumPyro as examples of probabilistic programming languages, which allows us to build complex probabilistic models for our different scientific needs. So we've introduced the challenge of dealing with farm-thread maps, and we've introduced probabilistic modelling and probabilistic programming as a way of getting out more information from these types of models. But why am I using this approach for XID+? Well, we've got domain expertise in confronting these farm-thread maps. We do have spatial positions of galaxies from other wavelengths observed in either the optical, the infrared or radio. For a lot of those galaxies we have more information, such as the redshift coming from photometric redshifts. We also have some idea of the functional relationship between wavelength and flux for galaxies, something we call spectral energy distributions. And we also have some idea of the statistical relations relating these galaxies to each other, such as luminosity functions. So if we want to get as much out of the data as possible, we should be using this domain expertise. It's this probabilistic approach which allows us to transparently input that prior information we have on the spatial positions, redshifts, SEDs and other statistical relations. The other key point, as we saw with the correlated posterior probability distribution example, is that producing catalogues is lossy if you're dealing with parameters which are correlated. Now for Herschel data, because sources are close together and you have a low resolution, you tend to find a lot of these posterior probability distributions are correlated. So the process of producing catalogues, then fitting SEDs independently, is lossy. The ideal approach would be to do all at the same time. So far we've had different iterations of XID+. For the Herschel Extragalactic Legacy project, we built up the framework for XID+ and used positional priors with some simple uniform prior distributions on the flux with sensible lower and upper limits. And it's this version we use to produce multi-wavelength catalogues for the Herschel Extragalactic Legacy project. William Pearson extended the idea of priors further by using something we call more informative flux priors. And here he moved from uniform prior distribution on the flux to a Gaussian distribution coming from SED fitting at other wavelengths. The latest iteration of XID+, which we're calling XID+ SED, incorporates SED fitting simultaneously using an emulated version of Segal. This is advantageous because it introduces wavelength dependence across the maps, such that shorter wavelength maps of higher resolution and other information such as photometric redshift can help take into account the correlation and degeneracy information and get more accurate values or estimates on the physical parameters. The other videos in this series will demonstrate how to run XID+ with positional priors and how to run the latest iteration, XID+ SED. And finally, how we've gone about building the probabilistic models for these different versions and how you could develop it further for your own science case. Thank you for listening.